Hello dear students, welcome to Pen and Paper Chemistry. As we continue with our topic on solutions, we have already spoken about quite a few definitions, and with this video we shall be continuing with our learning regarding some more interesting definitions like mole fraction, mass fraction, and molarity, molality, and the relationship between them. So please make sure that you have your pen and paper in place so that you can also practice some questions when we go along this particular topic. You will also find these notes on the Google site Pen and Paper Chemistry, but make sure that you write them at least once in your own hand. So let's get started. Okay, now before I go on to the next set of definitions, mole fraction, mass fraction, and so on, I want to put a simple question to you. Supposing you have 5 oranges and 6 apples. My question to you is, what is the fraction of oranges you have? Oh, yes. Very easy question, right? 5 by 11. And what is the fraction of apples you will have? 6 by 11. Very right. So we are going to apply this very knowledge to understand mole fraction and mass fraction. So if I say what is the mole fraction of solute in a solution, so that would be simply the number of moles of solute divided by the total number of moles in solution. What's the big deal about it? That's what you did over here. So what is the fraction of oranges? So number of oranges divided by the total number of fruits you had. The same logic we've applied over here, and we can also similarly determine the number of moles of the solvent. So here I am talking about a binary solution, a solution which is made up of 2 components. They could be 2 liquids, they could be a solid dissolved in a liquid, any. So if you have N1 representing the solute, then the corresponding mole fraction is denoted by X1. That would be the number of moles of solute divided by the total number of moles in solution, that is solute plus solvent. Similarly, the mole fraction of the solvent, X2, would be number of moles of the solvent divided by again the total number of moles in solution. If you have a ternary solution, that means a solution which is made up of 3 components, then in that case our numerator as well as denominator will be written like this, and N1 upon N1 plus N2 plus N3. It's a ternary 3 component solution, right? So number of moles of each component will be given, the mole fraction of each component will be given by the number of moles of that particular component divided by the total number of moles in solution. Coming back to a binary solution, what about adding the mole fraction? So N1 upon N1 plus N2 plus N2 upon N1 plus N2, add them up, what do you get? Yes, correct, we get it equal to 1. That means the sum of mole fractions in a solution is always equal to 1. Now what do you think would be the unit over here? Yes, there will be no unit. It's a simple pure ratio, right? You are talking about a ratio. The ratio of oranges to apples is 5:6, right? That is how you ended up writing 5 by 11 and 6 by 11. So the same thing applies over here. This will not have any unit. It will be a pure value. Apply the same fundamental when you are talking about mass fraction. That means the mass of component A divided by the mass of each of the components A, B, C, D, how many components you have in a mixture. Again, It will not have any unit. It is a pure fraction. Please, again a request, write down these notes yourself in your own handwriting so that you have better command on the topic. Let us now try and apply what we have learned regarding mass fraction, right? So if I give you a question over here, that 0.4 milligram of salt, say common salt or any salt, is present in 1 kg of an aqueous solution. So that solution is of the salt only. What is the mass fraction of the salt in the solution? Yes, please. You need to get your pen and paper out so that you can do this question, and then we will tally our answers. And I am also going to teach you how to attempt any numerical confidently. What are the steps? So you can pause the video, try this question yourself first. So let us start. If you see in this question, you've been given the data that there is 0.4 mg of salt. So that means I have been given that the mass of salt is 0.4 milligram. Then you also see that the mass of solution, be very careful what is given to you, the mass of the solution. So we will have over here, mass of solution is 1 kg, right? Now can I compare the two? Very easily we will say mass fraction is equals to the mass of the salt divided by the mass of the solution, and you get it as 0.4. Now did you get this answer? Then this is not the right way. Why? See over here, you've got the mass of the salt in milligram, whereas the mass of the solution is in kilogram. So you are comparing a mouse to a giant, right? Look at the milligram and the kilogram. So we need to get them at the same level. So how do we do that? So let us convert first both of them into gram. Let us bring them into a common platform so that we can compare them, right? And 1 kilogram is 1000 grams. So I can write it as 1 into 10 to the power 3 grams. Now they are on a level playing field, right? So it is easy. It is more sensible to do that comparison now. Go ahead now, do your calculations. So this is 0.4 into 10 to the power minus 3 divided by 1 into 10 to the power 3. So this gives me 0.4 into 10 to the power minus 6. What unit should I put? Yes, absolutely. We spoke a while ago and we said that since the units are same, it is simply a pure fraction. Now you see over here, I have to deal with such minute quantities also as at times, right? As a scientist, or when we are trying to find out the contaminant in a let's say a river is contaminated by some chemical. So what is the level of contamination? Now if I have to say 0.4 into 10 to the power minus 6 is the contamination level, it becomes very tedious, right? So what we did was, we, instead of saying it like this, we compare it to a value of 10 to the power 6. That means how much is the component, that is the mass of solute or mass of component in 10 to the power 6 parts of the solution. And what is this 10 to the power 6 known as? What is this suffix known as? Yes, absolutely, it is known as million, right? So we have our next definition in place. So parts per million. Parts per million means the amount of the solute in a million parts of a solution. So what do I have to do? I simply have to multiply this value by 10 to the power 6 and I will have my answer in ppm. Isn't that so much easy, right? So I will simply have to say that there is 0.4 ppm of salt in the given aqueous solution, right? So it makes my mention as well as comparison easy. To make it easy for you to remember, and if you are the one who wants to use formulas, then you have the mass of solute divided by mass of solution into 10 to the power 6 gives me ppm of solute. Okay, question. What would be ppb? Yes, absolutely right. That would be parts per billion, right? So that means multiplied by, find out, let's see. Let us now talk about molarity, normality and molality. Just be very careful about RITY and LITY over here, because that makes a lot of difference to the way we define and understand it. Molarity, simply put, is the number of moles of solute in a given volume of the solution expressed in liters. So if I am saying that a solution is 1 molar, that means I have 1 mole of solute present in 1 liter of the solution, right? On the other hand, when I speak about molality, that means again I have got 1 mole of solute. So it is the number of moles of solute present in 1 kg of solvent. So again, if I am saying that a solution is 1 molar, usually represented by a small m, that means I have got 1 mole of solute but in 1 kg of solvent, right? So you can very well see the differences. 1 mole is the same in both of them. Here we are talking about the volume of the solution, whereas in the case of molality, we are talking about the mass. In the case of molarity, I am talking about solution. In the case of molality, I am talking about solvent. So let us now further expand on the formulas that we have given over here. Molarity, denoted by capital M, is number of moles of solute present in 1 liter of the solution, or if you have the solution any other value, then you will simply divide to determine it per liter. Now, number of moles we've done earlier is the amount of solute in grams divided by the molar mass of the solute, and the volume of the solution in liters remains in place. Amount of solute in grams divided by volume of solution in liters. What does this remind you of? Yes, strength in gram per liter. In other words, what I can do is I can express this part of the formula as strength divided by the molar mass of the solute. You do not need to learn all the formulas. If you understand the basic and you got the formula chart in front of you, the basic formula chart, you will be able to derive any of these formulas yourself, as long as you understand the fundamentals. That means the number of moles of solute present in per liter of the solution. And you will understand more of this when we attempt a few numericals. Molality, the number of moles of solute present in 1 kg of the solvent. So if I have to determine per kg, I will divide the number of moles of solute by the mass of solvent. Yes, over here, see, we are talking about the solvent, and the mass of it in kgs. Again, expanding on the formula, number of moles of solute is mass of the solute in grams divided by the molar mass. Now you look at that, there's 1,000. Did I put it by mistake? Look very carefully. Look at the formula that we've got over here. Mass of solvent in grams. That means usually you are given the mass of solvent in grams when you work in the laboratory. We usually don't work in kgs, right? We work in grams. We talk about smaller amounts of the solvent and the solutions. So to make this formula easy to substitute, if we have been given the mass of solvent in grams, we will convert it to kg. And how do we convert it to kg? By dividing by 1000. But when there's 1,000 in the denominator, we will take it to the numerator, and that is what we have exactly done here, right? So I hope this clears the doubt regarding the 1,000 value over here. Remember, we are taking the mass of solvent in grams over here, right? Okay, so we've got two formulas for molality, or just one if you have understood what it is about. The question arises, if I have got molarity, why should I bother myself with molality? Why should I add one more thing to my learning? You see over here, we've got volume of the solution. Now, volume is, or mass, volume is equals to mass divided by density. So what happens is, when we are talking about solutions and there is a range of temperature over which we have to observe the variation of concentration or some variable dependent on concentration or molarity, then in that case there are large changes in the concentration with change in temperature. So temperature changes, M changes, molarity changes. But in the case of molality, we are talking about mass. Now, the mass remains unchanged. There is not a very perceptible, no large change in mass with change in temperature. So that is why when we have to observe certain variables with regard to changes in temperature, or we have to keep the concentration variable constant, but do measurements over large temperature changes, then we would prefer molality instead of molarity. Now the question arises, what will be the unit of each one of them, molarity and molality? Although I have written it very clearly, molarity, R-I-T-Y, is denoted by capital M, whereas molality is denoted by small m. But what does capital M or small m mean over here? Let's break down what we've got. So we've got a value of the number of moles. Does number of moles of solute have any unit? No, it's a pure number, right? So mass divided by molar mass. So I will simply put over here moles, right? And what about the volume of solution? That is taken in liters. So we have the unit of molarity as moles per liter. Now sometimes you may also come across moles per decimeter cube. Even that is fine, because we know that 1 liter is the same as 1 decimeter cube. Of course, if the values are given, if the volume unit is given in some other value, let's say centimeter cube, then in that case you know the relation 1 liter is 1000 centimeter cube or cc, and that will help you to convert into the corresponding liter value. When I talk about molality, now this again is number of moles, so I will simply put it as over here moles, right? Mass of the solvent in kg, so this will be, the unit would be moles per kg, which is also written as small m. Now, in between molarity and molality, you will see over here a small tiny bit of normality written over here, squished between the two. Now, this is a term which is not very commonly dealt in most of the curriculum, but we will talk about it just to keep you informed about what it is. In the case of normality, we talk about the number of gram equivalents of solute divided by the volume of solution in liters. That means the number of gram equivalents of solute per liter of the solution. In other words, what we mean is normality is mass of solute divided by the, instead of the molar mass, we will say the equivalent mass of solute. Now, what is equivalent mass? In this particular video, we will not go into the details of this. We will do it as a separate task. Divided by the volume of solution in liters, right? Again, I can take mass of solute upon volume as strength in grams per liter. So, I can write it as strength in gram per liter divided by the equivalent mass of solute. Again, be very, very careful about the terms solute, solvent and solution. I hope you are noting these down for future reference. The next thing that we are taking up is the relationship between molarity and molality. That means if one is given, how do you determine the other from it? And to understand that, I would request you to keep your pen and paper with you and do the derivation with me step by step in order to understand it more better. Because we are going to learn how to derive this formula rather than just memorize. Yes, you can memorize in the end, but it is better to understand how we do. So let's get started. We have been given that the molarity of a solution is M, and I am denoting it by capital M. And the density of the solution is d gram per cc. That means this is given to us. We know these values, right? So I'm going to derive, I'm not taking any specific values over here. Let's break down these values in terms of what we know. Molarity M means M moles of the solute in 1000 cc of the solution, right? So that means I know over here, first of all, I know the volume of the solution, okay, and I have also been given the density of the solution, which is d gram per cc. So volume into density gives you, yes, absolutely, the mass. So we get over here the mass of the solution is the volume of the solution, which is 1000 cc, multiplied by the density, which is d, and we get the mass of the solution in grams. Now I need to determine the mass of the solvent. Remember, molality is all about the number of moles of solute divided by the mass of solvent in kg, and if this mass of solvent is taken in gram, then I need to convert it into kilogram by dividing by 1000, right? So let's go back to the number of moles, M moles of solute. If the molar mass of the solute is given to you, or you know what is the solute, so mass can be easily determined because number of moles is, so this is number of moles capital M, that will be mass of the solute, molar mass divided by molar mass. So mass of solute is the number of moles into molar mass of solute. Step by step. Solute plus solvent gives a solution. So what will be the mass of the solvent? Equation 1, equation 2. I subtract equation 2 from equation 1 and I get the value of the mass of the solvent, which will be 1000 D minus the molarity. Remember, the capital M over here stands for molarity, times the molar mass of the solute. So 1000 D minus M into molar mass of the solute. If you want, you can mention it as SOL over here. Now, we have to determine, don't forget the main target, we have to determine the molality. Molality is given by the number of moles of the solute divided by the mass of solvent in kg. So number of moles of solute is M, capital M. How do we know that? M moles of solute present in how many grams of the solvent? 1000 times D minus M into molar mass. But according to our definition, we have to take it in kilograms. So I will multiply it by 1000. So you get one formula over here, that is molality is molarity. So what I will do is I will put over here molarity times 1000 divided by 1000 D minus again molarity into molar mass of solute. Now this sounds confusing, right? Because we've got molarity into 1000 and we've got molarity over here. So what we do is let's take the reciprocal of this equation. So let's flip this around. 1 upon molality is 1000 D minus M into molar mass of solute divided by molarity into 1000. Remember, again our capital M is molarity. I think for the sake of clarity, I will put molarity only over here, right? And this also is molarity. So remember, we flipped both the sides. Numerator becomes denominator, denominator becomes numerator. So we flipped. Now that means I can divide. If you are not confident about deriving the next step, you can always remember this formula or definitely go logically. So first find out mass of solution, mass of solute and mass of solvent. Substitute in the formula for molality. You can also do it that way. You can also learn this formula over here. So this is a formula for you if you are a formula person. Alternately, as I said, we flip this and divide each of these by molarity into 1000. So if I divide 1000 into D by molarity into 1000 minus molarity into molar mass of solute divided by molarity into 1000. So again, I can do away with the 1000 over here and molarity over here. I am left with a simple formula. 1 divided by molality is density in gram per cc divided by molarity minus molar mass of solute divided by 1000. This gives us formula number 2. You can either learn this or you can learn the formula number 1, or you can also move logically. Now many a times students do find this quite intimidating. So what I will do is I will take up a few questions on these formulas, on these definitions that we have learned so far, so that you can gain confidence on the topic. In the meantime, what do you have to do? You have to take a pen and maybe take sketch pens So I would say colored pens and an A4 sheet or an old calendar, my favorite thing, and write down all these formulas on that so that you can revise them daily. Revise them, write them, and you are good to attempt any kind of numerical as long as you understand how to attempt a numerical. So if we first write down the data, we check the units, we apply the formula, substitute the values, the answer with the units. So first step is data, second step is check units, third step is formula, fourth step over here is substitution, and fifth step of course is our answer but with the correct unit in place, and you are good to go in this topic. See you in the next video soon. Till then, enjoy your learning journey with pen and paper chemistry.